Please welcome Qkera, Technical University of Munich Entrepreneurship.
Ladies and gentlemen, what a magnificent vibe today in this room. My name is Qkera. I'm the head of entrepreneurship at the Technical University of Munich. In a world where renewable energy is increasingly vital, the startup Qkera offers a unique material platform designed for next-generation batteries, utilizing competitive and CO2-reduced production methods. It is crucial to gain global independence in green energy storage and manufacturing in order to ensure socio-economic stability. Here, the European startup Qkera provides novel battery tech. The Munich-based startup is led by CTO Andy Wise and CSO Jennifer Rupp. And today we have Jennifer, who represents only 6% of female founders in deep tech, here with us. Jennifer is a professor at the Technical University of Munich and has previously taught at MIT and ETH Zurich. She is the youngest and only female member of the energy division of the National Academy Leopoldina. And Jennifer has received numerous awards, including being named a recent Max Planck Fellow, as well as industry recognitions from numerous companies like BASF, Volkswagen, Merck, Samsung, and many others. Qkera is based on proprietary technology, as well as further developments from the Rupp Lab's intellectual property and innovation. And now, please welcome with me on stage to break walls in novel battery tech, Jennifer from Qkera.
Breaking the wall to safe and powerful batteries. Jennifer Rupp, Qkera.
Yes, so hello everyone. I have some really good news to share with you. The world needs about 170,000 terawatts and gets those as free energy by solar and wind every year. And if we think about it, the total human being needs about 23 terawatts per year. So the question is not, do we have enough renewable energies? We do, we have it. The only challenge is, how do we make it storable? And how do we make it storable, and I would say that was yesterday's news, that it's socio-economically acceptable with elements that you can mine close by and make accessible for our society. When we think about it, then every time we have an electric vehicle, you reduce your personal footprint by 50% compared to a combustion car. So there's no argument that we should go in mobility towards electric verifications with cars. Now, where's the challenge? Well, if we want to have a larger reach with your car, then you can actually increase, and that's another really good news, by using pure lithium as anodes, you reach by about 30% higher energy densities and longer wide distances. The other challenge is, if we want to use lithium, we have to make a U-turn and a change in thinking, and that's what Qkera is about, and what materials to enable this transition. Also, we enable with our technology at Qkera as an electrolyte platform technology to use actually less elements that have socioeconomical critical elements like cobalt, for instance, in the future batteries. So what is it all about? And I want you to take home two numbers here. So when we look here at this plot, in a classic lithium-ion battery, and all of you have one on you today here in this room, will have about like 750 watt-hour per liter, and you can get it actually at a price tag of about $120 per kilowatt-hour. So where's the challenge? This number, either in price, will not further go down, and also the energy density will not further increase unless you come with new materials. The other challenge is that in the battery, you have some liquids. The moment I crack your battery open in your phone, it will start to inflame, and it's no fun to have a lithium fire. Go for other fires, guys. Okay, so what is there to be done? Well, with exchanging materials, enabling to have solid-state battery electrolyte materials, and I bring you here one from Qkera. It's really tiny. It's actually not even this plastic you see here. It's a ceramic coated on top that is smaller than one hair that I have with me. Right? Then you can enable actually to reach 30% higher energy density. If I go to the plot before, and you can come actually to 1,100 watt-hour per liter. But to do so, you have to match to strongly bring down the existing prices in the market, and that is where we set our technology to come to competitive prices, enabling the higher energy density. So at Qkera, we developed so-called solid-state lithium electrolyte. It's a platform technology where we can bring a different TRL level to different battery designs, those type of teeny tiny electrolytes as a solid. So you can see that it's an open air, it doesn't inflame, right? Compared to this one here, which if it were to be a lithium with a liquid, it will inflame. And we can enable to bring that in different battery designs. So this is an example of a car pouch cell battery prototype here. And we can integrate that, and with that actually later enable the next generation of batteries with 30% energy density. And this needs the solid-state electrolyte material to bring in pure lithium and socioeconomic friendly elements on the cathode side. So where is that at, and why is that actually so special? Why hasn't it been done before? So at Qkera, we have proprietary intellectual property that actually enables us later to have, through our invention, the first time an area coating that is in the spec of where you need to be for a battery electrified coating that you have when you want to integrate it, which is about 10 by 30 square centimeter, for instance, later for such pouch battery cells. Now, to get there, the field before had different other oxide components like our ceramic lithium electrolytes, but they didn't manage to have actually a scale-up and a roll-to-roll processable technology, making so thin, tiny electrolytes like you see here. That's the size of my hair. That's an example of a Qkera electrolyte, and bring this lithium ceramic solid-state electrolyte as a platform technologies on as much as possible. And I mentioned the word ceramic, so you may think, well, my ceramic coffee cup, think about this thing about hole with lithium. And normally that's stiff. And I can take this, and I can scribble this. It's on it here. It won't break. Yeah? So it doesn't fire up. It doesn't break. You can come to these areas. And with that, we want to contribute to breakthroughs in energy storage. And it's an enabler to use the 30% high energy density lithium. And on the other side, the only combination that we know of worldwide to enable actually cathodes that have cobalt reduced and other conflict-free elements. And we believe this is very important, especially in a climate where we should think about what to use. And with that, I come to the end, and I'm very happy to take your questions. Thank you.
I have a double timer to check the time double, so
Great.
you have no chance to go
Great.
further. Okay, so we have here 2 questions from our juries. Please come on, Michael.
Yes.
Thanks a lot. With which corporate partners are you planning to run down the cost curve?
Yes, so I think that goes back to different battery manufacturers. So ideally, we are a platform technology. We want to be in as many designs as possible. And the cool news is we can go at a medium TRL level in hybrid energy battery systems, where we can enable with the solid-state electrolytes the other materials. Or it can also be a high TRL level, for instance, going there in existing lithium-ion batteries, adding that on a polymer like I just showed you. And there is now different corporate partners that we are looking at on the battery manufacturing side, but then also co-partners on the material side. For instance, companies working on lithium that want to spread it to the market, as well as on the cathode side. Yeah.
Thank you. Next question.
Thanks for presentation. I am just wondering about the difference on this technology compared to this what Prologium is bringing in France now as well. 5 billion was invested. They are bringing the ceramic solid-state battery in 2 years to the market. Where is the unique point on your technology compared to this what is already existing?
That's right. So Prologium, and that's quite different, is working on a technology where they have a ceramic that is sintered, so it needs extremely high temperatures, so the footprint in carbon dioxide will be at least 50% higher than what I showed you here, because it's a thin film technology that comes directly from a liquid going directly in a solid film. Also, we are a factor of I think about 10 to 100 smaller. This enables to have more volume for the electrodes and the battery settings that you see for whatever design you have. The other part is cost. So every battery here in the room has an electrolyte which costs about $2 per square meter. And most of the ceramics out there that are there based on oxides are around more like $7 per square meter. What I showed you is at around 1.8. And I think cost is important. If you don't break that, and that's where we come as a new tech, you can't go and enter the market. But I think that's why I believe the combination is very good.
Yeah. Iris?
Thanks, Jennifer. Very interesting. I was wondering if you could comment a little bit on the results from the performance test done with the pouch cell prototype. So you mentioned energy density of more than or 30% extra already, which is great, of course, for mobile applications. But I was wondering, what is the number of cycles tested, and do you have any like thoughts on like round trip efficiency and things?
Yes. So in general, I will differentiate your question in two parts. So the field has demonstrated that 1,100 watt-hour per liter are feasible for full solid-state battery designs. It doesn't need to be one. It could also be a hybrid with some liquid, higher TRL level. And I think in our test, we have done them together with Samsung. So Samsung has been a sparring partner of my labs for many years. And there we run them for a bit more than a couple of hundred cycles, so not excessive. And we had about 80% capacity retention. But it was a different battery design than a pouch cell.
Okay, Stefan, please.
Is there? I mean, there are a lot of advantages in your production. Is there also one disadvantage? If you could talk about that.
Absolutely, great question. Thank you so much. Yes, there is, and that is, let's face it, in Europe, there's 80% of battery market in Asia. So we are a startup racking up, and our biggest competitor is actually companies currently dominate in Asia, where also the elements are from. Now, I think this is, for us as a startup, sometimes hard, because you have to break the wall anyhow to go through that. But my answer to this is it's really important we do it on space, because we want to enable to use elements we can mine close by to bring them and do not close down on battery manufacture and making new materials really as deep tech in Europe. And I think that's something that I see as the biggest hurdle on many levels, but I will not keep down the fight for that.
Okay.
Yeah.
Thank you very much.
Thank you.
Punkt Landung. This is great. It's not going to explode, no?